Section 11.1 Goodness of Fit. In this section, we are trying to test the hypothesis if the given data fit into a certain distribution. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits some claimed distribution. O represents the observed frequency. E represents the expected frequency. K represents the number of different categories or cells. N represents the total number of trials. P represents the probability that a sample value falls within a particular category. The requirements for goodness of fit. First, the data have been randomly selected. Second, the sample data consists of frequency counts for each of the different categories. Third, for each category, the expected frequency is at least 5. Here is the hypothesis for goodness of fit test. For HO, the frequency counts agree with the claimed distribution. HA, the frequency counts do not agree with the claimed distribution. The difference between HO and HA here is that HA is always the statement saying that is agree with whatever distribution, and HO is the statement saying that they do not agree. Here is the formula to find the test statistic. This is called chi-square. To find the value of chi-square, I'll take the summation of the observed frequency minus the expected frequency square divided by the expected frequency. However, we will use technology to find this number. For p-values, I will also use technology for this. Example 1. A random sample of 100 weights of Californians is obtained, and the last digits of those weights are summarized in the table. When obtaining weights of subjects, it is extremely important to actually measure their weights instead of asking them to report their weights. Test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. I'm given a table. This column represents the last digit of the weights. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If my weight is 120 pounds, the last digit is 0. If my weight is 133 pounds, the last digit is 3. If my weight is 199 pounds, the last digit is 9. I have 10 different categories or 10 different cells. This column is the observed frequency, which is the frequency when I weighed this 100 people. I found out that 46 of them have the weights with 0 as the last digit. 30 of them have the weight with 5 as the last digit. None of those have the weight with 7 as the last digit. Expected frequency is found depends on the question that they ask me. In this question, they ask me to test the claim that the sample is from a population of the weights in which the last digits do not occur with the same frequency. My expected frequency would be the same for every cells. I have total of 100 people. If I add all of these frequency up, it should be 100. And total of 10 different cells. And I want to have the same frequency on each cell. What I would do is take 100 divided by 10. Because this question was asking me to test the claim if the last digit do not occur with the same frequency, that means I want my expected frequency to be the same. Expected frequency does not have to be the same on every problem. It really depends on what they're asking you. And I will use the observed frequency and expected frequency to calculate for my test statistic and my p-value. The process for the hypothesis test is going to be similar to what we've been doing. I have my hypothesis, significance level, test statistic, p-value, decision, and conclusion. For the hypothesis, I'll go back to my original claim. Test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. This one should be my HA because it's the negation, because HO should be the one that the data agree with a certain distribution. HA is the one that do not agree. So this is going to be my HA. HA is the statement that the data do not occur with the same frequency. HO will be the statement stating that the given data occur with the same frequency. Significance level is not given, so I will use 5%, and I will use StatCrunch to find my test statistic and my p-value. I have already imported the data into StatCrunch. The first column is the observed frequency. The second column is the expected frequency. I am going to click on Stat, Goodness of Fit, chi-square test. Observed column, I will select the first column. Down here, you will have two options. If you have your expected column, you can select the expected column. If not, you can click on here. You have this option for this problem only because all the cells are equal proportion. We have all 10 in all cells. If they are different, you have to have your own expected column. If they are the same, you can also click on here. This is your test statistic and this is your p-value. Test statistic is chi-square equals 212.8. For the p-value, they don't give me the actual p-value. They just say that my p-value is less than 0.0001. If the p-value is less than 0.0001, it's also less than 0.05. So I do reject my HO. I do reject HO. That means I don't think HO is true. That means I think HA is true. That means I think that the sample is from a population of weights in which the last digits do not occur with the same frequency. Example 2. According to Benford's law, many data sets have the property that the leading digits follow the distribution shown in the first two rows of the table below. The bottom row lists the frequencies of the leading digits of internet traffic inter-arrival times. Do the frequencies in the bottom row fit the distributions according to Benford's law? The first row is the row of leading digits from 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 different categories. The second row is the row representing the Benford's law. Benford's law says that 30.1% of the population will have the first digit of 1. 17.6% of the whole population will have the first digit of 2. 9.7% of the whole population will have the first digit of 4, and so on. The third row is my sample. I have 69 number have the first digit of 1. 40 number have the first digit of 2. 16 numbers have the first digit of 6. The question asks if this sample is from a population fits the Benford's law, which is 30.1% will have the first digit of 1. 17.6% will have the first digit of 2. This is the row that I'm going to put in my expected frequency. Expected frequency is the frequency that I'm expecting to have 31% that have the first digit of 1. To do that, I'm looking for my total sample size. I'm going to add all of these up. My N is 271. And I'm expecting 30.1% of 271 will have the first digit of 1. So the first cell of my expected frequency should be 31% of 271. And I get 81.571. The second cell of my expected frequency is 17.6% of 271, which is 47.696. The third expected frequency cell is 12.5% of 271. The fourth cell is going to be 9.7% of 271. The expected frequency on this one is going to be 7.9% of 271. For this one is 6.7% of 271 and 5.8% of 271, 5.1% of 271, 4.6% of 271. The question asks, do the frequencies in the bottom row fit the distribution according to Benford's law? This is going to be my HO. HA would be a statement saying that the frequency in the bottom row do not fit the distribution according to Benford's law. Significance level is 0.05. And I will use StatCrunch for my test statistic and my p-value. This is my observed frequency, and this is my expected frequency. Stat, goodness of fit, chi-square test. Choose the correct observed column. For the expected frequency, I cannot use this option since all of these cells are different. I have to have the expected column. This is my test statistic and this is my p-value. Test statistic is chi-square equals 11.279177. Please read the instruction to see how many decimal places that you have to round to. I am going to round this to 3 decimal places. And my p-value is 0.1864. P-value is greater than alpha. I will not reject HO. I do not reject HO. That means I believe that the frequency fit the Benford's law.